kind of part of our philosophy of building these things, and also gives you a hint as to how you might basically try this at home. So this is one of the very first times that we made the robot open a door. This is actually an alpha robot. It's hard to tell here, but it only has one arm. And so we got the robot to open the door. That was great. And then, let me see, let's just jump forward to here. Here's the robot plugging in. One of the very first times you made it plug in. You can see it plugs in forward instead of sideways. You can also see that it took a bunch of different tries to plug in. I'll come back to that point. What is important about this is that, so we got it to do those two things, and we ran what we thought was a pretty impressive experiment. We gave the robot the task of going and plugging itself into 10 different outlets all around the building, most of them behind doors. So it had to go to all these offices, open the door, go in, plug itself in, unplug, and go on, all uninterrupted, with no help. It did that. About a week later, we tried to do it again, and it didn't work anymore. Right? This was this problem of the bits had basically rot. People had made changes, and the stuff just didn't work anymore. And this is a really, really common problem. So one of the ways that we decided to address that was essentially testing. So if you've done any engineering work, you know that it doesn't work unless it's tested. Testing these kinds of systems, especially these complex tasks like opening doors, plugging yourself in, it's really hard. So one of the ways that we do that is we use simulation. And this is one of the ways that you could play along at home, if you will. Along with all the rest of our open source software is a 3D, physically plausible, reasonably realistic simulation of the PR2. So one of the things we did after we got it to open doors was we made it open doors in simulation. So what you're seeing here is, you can see the laser scanner here is tilting. It's taking a nice slow scan of the door, trying to find the handle. The important thing is that this is exactly the same code that runs on the robot. The interface with the physical robot and the interface with the simulation is identical. We're running the whole thing. We're taking simulated camera views, and we're doing stereo processing on that and extracting depth. We're taking the laser scan, examining the point clouds, segmenting out the handle, figuring out where it is. We run the same controller on the arm, and it goes out, and the gripper closes, and it opens. We kind of fake the turning of the handle, but because some of these things are difficult to simulate. But it's using the same navigation system to drive through, while avoiding, keeping the arm far enough out to avoid hitting the door with the base, and so on. This is now a regression test. So we have a lot of code, an enormous amount of code written by a lot of people, and people might change a lot of the parts of the system that underlie this demonstration. So every time someone checks in a change to the code, there's an automated system that checks it back out, builds everything, and runs this simulation, and checks whether, at the end of it, did the robot end up on the other side of the door. If it did, the test passed. If it didn't, the test failed. That's a big flashing red light, and we go back and look at the changes and we figure out what happened. So this is a necessary but not sufficient test of this demo. We know that if it doesn't work in simulation, it's not going to work in the real robot. We did the same thing for plugging in. So this is a simulation of that sideways plugging in. You can see the arm going out. At the time, we didn't have a simulation of the texture projection when we made this video, which we do now, but we just faked it. We just painted texture on the wall in simulation. That works just as well. But we're actually doing stereo in simulation. So we're asking the graphics card, give me the view of the world from these two cameras, and then we run exactly the same stereo algorithm on that simulated data and get the plane of the wall. And that's really important. To make these tests meaningful, we have to be running exactly the same code. Otherwise, we're not testing the system. If we let this run long enough, it'll actually, and again here, it actually uses the forearm camera to find the checkered plug, and it goes and plugs itself in. And this is a regression test. And these are some of the best tests that we have of the whole system. So we do testing at a very low level. You make sure each piece works. But to understand whether any given system that you've built will work together, when it's a pretty complex distributed system, right? To run this task, you're talking about, I don't know, on the order of 50 processes, all running in parallel, all doing different things, looking at the vision, controlling the arms, and so on. And to make sure that the interaction of all those processes in parallel results in what you want, you have to test it.